Hey there! In this video, we'll finish up our section by learning a little bit about how to approach integrated spectroscopy and mass spectrometry problems. All right, so the whole point of learning about mass spec is that it complements our other spectroscopic techniques like IR and NMR. It tells us how we get the formula, and it can also give us some additional ideas about functional groups and isotope patterns that can help us in tricky situations. But realistically, it's better to just have that full picture. Now, whether you're isolating natural products from things like sea sponges or dreaming up brand new molecules and then trying to make them in the lab, it's really important to have techniques like IR, mass spec, and NMR to confirm the identities of the structures that we've isolated or made. And the thing about all of these different techniques is that they are more than just the sum of their parts. When we take them together, they provide us a greater wealth of information than any of them could on their own. So we're going to get some practice doing what we'll call integrated problems. Now, this is where we analyze data from most or all of these techniques and synthesize our findings to try to determine the structure of a compound or, something about it. Now, this is really no easy task, and I know that, this is a really kind of unfamiliar territory, and it might seem a little bit nerve-wracking. So it helps us to take a stepwise approach when looking at problems of this type. And I promise you, spectroscopic analysis and structure characterization can be really fun, but it does take a lot of practice. So we do have at the bottom here, I just want to recommend before we get into the method. This is a great website for lots of different integrated problems, and there are also lots of integrated problems in the workbooks on our My Courses page. So I really recommend taking some time to practice those because honestly, the only way to really learn how to determine structures is by practicing lots of problems of this type. Alrighty, so here's what we're going to recommend for how to piece all of this together. So first things first, we're going to look at the pieces of data that give us less information. And then we're going to build on that information by looking at our more and more complicated spectra in turn. So in this respect, it's always a good idea to start with your mass spec. And this is especially true if you don't have a molecular formula. Now from your mass spec, you can get clues about things like the molecular weight or the formula of your unknown compound. You can figure out the max number of carbons in your compound, and you can also determine if there's any heteroatoms like chlorine, bromine, sulfur, or nitrogen in your compound. Then we can move to IR. Now this is going to tell us about obvious functional groups like carbonyls. Unfortunately, not too much more than that. But even with those two pieces of information, we are already on a much stronger footing to start looking at our NMR spectrum, because we now have some clues about what exactly it is we're looking for, rather than going in totally blind. Then we can turn to our carbon NMR. Again, there's not a huge amount of information here, but we're going to get a good idea of the number of different types of carbons and perhaps some clues about the different chemical environments that exist in our structure. And finally, the last piece of the puzzle and our workhorse, proton NMR. Now with this, we can really put those puzzle pieces together. Our proton NMR will tell us not just about how many types of protons we have in our molecule, but also the different environments they're in, how many of them are in each of those environments, and where their neighbors live. So it's a really good idea to take each of these things step by step because it is very easy to get overwhelmed. But once you've had a little bit of practice at going through this process, I promise it will become easier. So as our last thing, we will start out just by looking at a really simple example to get our feet wet. So here we've got a mass spectrum with some information about the IR spectrum of that compound provided in the text. Now we don't need to come up with the entire structure, we are just looking for the best possible formula. So in our mass spec, first let's look to our molecular ion region on the right. So we can see that we've got this group of signals over here, kind of around 130. And what we see here is that we've got a larger peak at 129 with this relative abundance of 30%, and a smaller peak at 130 with a relative abundance of 2.4%. And these are most likely to be our molecular ion, or our M+, and our M+1, because there's nothing else further to the right than that. Now, we can double check our assignment of our M plus by looking at the other fragments. So we know that we've assigned this M plus as being 129. Our M plus 1 is at 130. Okay. So let's look at those fragments. We've got a big one at, let's see, this is about 72. And we've also got our base peak, which is at 114. So both of these fragments have even mass numbers. And so this agrees well with having an odd mass for our molecular ion peak. And so we can say that, yes, it does look like our compound has a mass of 129 mass units or grams per mole. Now, before we move on, there are a few other bits of info we can get from our mass spec. So first things first, we see that our molecular ion peak is odd, and this suggests an odd number of nitrogens. So could be 1, 3, maybe even 5. That seems a bit crazy, but hey, we'll keep it in mind. All right. Second, we don't see anything interesting with respect to isotope patterns like those for chlorine, bromine, or sulfur, but we do have this small M plus 1 that probably results from C13. So we can kind of cross, chlorines and bromines off our list. And finally, we can use the relative abundances of the M plus and M plus 1 peaks to determine the maximum possible number of carbon atoms in our structure. So we've got those exact values, 2.4% and 30%. And again, all we need to do is calculate our ratio. So 2.4 divided by 30 times 100, and that is going to give us 8. So we will have no more than 8 carbons in our structure. So to sum up everything we've got from mass spec, our structure has no more than 8 carbons. We have an odd number of nitrogens, and we have a mass of 129 grams per mole. All right, now let's look at our IR data. So all it tells us is that we have a strong absorption at 1670 and nothing above 3000 wave numbers. This band at 1670 suggests the presence of a carbonyl group, and this means that our structure also likely contains an oxygen atom. No absorptions above 3000 wave numbers. Okay, well, let's think. This means no sp or sp2 CH stretches. Okay, so all of our carbons must be sp3 hybridized. But it also means no alcohol or amine stretches, because those absorptions are all around 3500. So this is kind of interesting because we know that we probably have a nitrogen atom in there, and this means that it can't have any hydrogens attached to it, so therefore it must be a tertiary nitrogen. So this is actually a fair bit of information, and I think it'll get us a long way towards putting these formulas together. So let's do a bit of trial and error and come up with some ideas and then calculate those masses. Again, we know that our final mass must add up to 129. So let's start with our 8 carbons. Okay, so if we have 8 carbons, again, we're using our exact masses to do this. So we multiply them by 12 mass units. 8 times 12 is going to be 96 mass units. For our oxygen, if we have 1 oxygen from that carbonyl group, multiply that by 16. Okay, that's an extra 16 mass units. If we put in an odd nitrogen, let's just start with 1, multiply that by 14 mass units, and we get 14. And so let's add that all together. We get a total of 126. Let's compare that to our overall mass that we know as 129. Well, that only gives us room for, let's see here, C8ONH3. Ooh, I don't think that 3 protons is gonna quite cut it for this particular molecule. So I think let's try again, because we do know that 8 is only the maximum number of carbons. So let's just try to go 1 down. Let's try again with 7 carbons. So for our carbons, 7 times 12, that gives us 84. For our oxygens, we'll stick with 1. That gives us 16. For our nitrogens, go with 1 again. That gives us 14. And when we total this whole thing up, that gives us 114. Now, when we subtract 129 minus 114, that gives us a remainder of 15 protons. And if we put that all together in our formula, CHONH15, it's already looking a little bit better, but what we can do is just go one step further and calculate the units of unsaturation. Again, we can go by the comparison method. We can go using the fancy formula. Regardless of what we do, we're going to see that we have 1 unit of unsaturation. And that 1 unit of unsaturation makes perfect sense because we know we're going to need one in that carbonyl bond. And so, I mean, we're basically done here. We could try to dream up all sorts of structures. Unfortunately, without more spectral data, we're not going to get very far in terms of determining an exact structure. But what we do know is that CHONH15 is certainly a very possible candidate for the formula of this compound. So that is it for our spectrometry and our spectroscopy section. And now I think the best thing for you to do is to just go out and attack as many problems as you can. Good luck.